Louisa does not want to die from the coronavirus, but more importantly, she does not want to fail her PChem exam. But what more can she do when studying is just not enough?
Hi everyone! In today's video we are going to be tackling the 1,3,5-trichlorobenzene and determining how many moles are IR active this molecule. Step 1. Determine the point group. For this particular molecule we have a D3H point group. After having that figured out, we can look up the associated character table. From the character table, we are going to be able to find the key gammas that we have to obtain. I got stage fright.
Keep moving. All right. 3, 2, 1, action.
Alright, so the first gamma we're going to have to find is gamma XYZ. And before we can determine what exactly this is, there's a few rules of thumb that we can follow. For that identity character, which is represented by E, it is always going to be 3, which is due to us having an XYZ axis. For proper rotations, we have the following formula here, which is given by Cn equals 1 plus 2 cosine 360 over n. And for improper rotations, it is the same formula, but with a slight modification as shown here. It would be Sn equals negative 1 plus 2 cosine over 360 n. And reflections are the easiest, as sigma is always equal to 1. And if you don't get that, take a moment to pause this video and reflect on it.
Unacceptable. Basically, using the key steps and tips from step 2, we know that E is 3, and for C3 it would be 0, and from C2 using this formula it would be negative 1, and then we know that this right here is 1, and this will be 2, negative 2, and this is 1. Yeah. To find the rotational gammas, basically your identity function remains the same. Additionally, your rotational or proper rotations also stayed the same. But the only things that change are your symmetry and your improper rotations. Negative 1, 2, negative 1. Why? Why does it change though? Why? Okay. So, to find the amount where I'm at out of the frame. To find the gamma, the number of unmoved atoms in this whole, for identity, it's 12.
Because none move.
Because none move. All right, moving on. For C3,
So 120
0. Everything moves
by 120 degrees.
by 120 degrees. Everything moves by 120 degrees. Okay, so we can see from a similar molecule, boron trifluoride, because we couldn't find examples of 1,3,5 trichlorobenzene. So a similar molecule, boron trifluoride, it's also D3H. For example, with the C3 rotation, we can see that all the molecules in it flip. So if you move it around, you'd see that the C3 rotation moves all the molecules, which would be the reason why the C3 would be 0 for this and 0 for the molecule in question that we are looking at. For C2, we have 4 unmoved atoms. Yeah.
Because it moves by 180 degrees.
Similarly, for the C2 rotation, we see that only a few of the molecules are moving at the same time. And if like these, the boron and this fluorine, for example, they stay where they are while the other 2 move. We can use this as imagery to look at the molecule that we are looking at. Sigma H12. For horizontal symmetry, we can see that nothing happens. It doesn't move at all. Improper rotation, S3, 0. Sigma V, 4. For the improper rotations, we see that once again, everything moves, which accounts for the 0. And the vertical reflection, we can see that once again 2 atoms are moving, so 2 atoms are staying constant. So if you think about it, looking at the molecule that we are looking at, the 135 trichlorobenzene, we notice that a few molecules would stay constant while the others move. So for gamma 3N, we multiply the gamma of unmoved atoms and the gamma XYZ. So for E, we have 36. For C3, we have 0. For this, we have C2, we have -4. For sigma H, we have 12. For S3, we have 0. And for sigma V, we have 4. For gamma Vib, it's gamma 3N minus gamma rotation now minus gamma XYZ. So it will be 36 minus 3, which is 27. Yes. Wait. Yes.
30.
30?
36 minus 3 minus 3.
I can't do math. 30 it is. Cool.
No, 0, so -4, -1, so -6, I believe. 12 minus 1, which is 11. Minus 1, wait, 12 minus -1, which is 13. Minus 1, which is, okay, 12. Cool. And then 0 minus 2, minus -2, 0. And 4 minus 1, minus 1. 4, which is 4. Cool. Hurrah. Yeah. We did it.
Let me know when to go.
Yeah, it's been going.
Alright, so now that we have the 2 key gammas that we're going to need to determine whether or not we have some IR active modes, we can now reduce. So referring back to our character table as shown here, we can see that gamma XYZ by inspection is equal to E prime plus A2 double prime. You can fact check me on that. And a key thing to note is that whatever's in your XYZ, if the corresponding character is in the reduced form of the gamma for Vib, then we are IR active. So we need to go ahead and check whether the reduced form of gamma Vib has either E prime or A2 double prime. And to do that, we have to reduce it as well. So referring back to our character table, doo-doo. So going to our gamma Vib, reducing, and with E prime and A2 double prime, we get the coefficients of 7 for E prime, 3 for A2 double prime. And all you have to do is add them, which sums to 10, and that means we have a total of 10 IR active modes for 1,3,5-trichlorobenzene.
So Louisa, are you ready for that final?